My name is ELAJEV. I'm from a company called ZeroTurnaround, and this session will be about Java bytecode. And mandatory disclaimer, there is an app for asking questions, voting on sessions. Unfortunately, I didn't find any way to answer the questions if you ask in there, so I would really prefer if you just forward those in Twitter, because there is no means to provide any answer. So you can find me at @ELAJEV, and we can connect that way. And also, I really will try my best to be on time. I'm really time-boxed because I have to go to the airport and fly. So we'll do this way. If you have any questions, let's keep it really interactive. So you just go whenever you have a question. I'm sorry, can I have a help of some of the organizers? Okay, good, thanks. The timer was off. So yeah, Java bytecode explain. We'll get there in a second. So about me, I work for ZeroTurnaround. As I said, I'm in the position of developer advocate currently. One of the main responsibilities that I have is to maintain and push forward the content portal called RebelLabs, where we publish our technologically advanced and opinionated content. So if you check it out, I'd be happy. And you can connect with me. ZeroTurnaround is a creator of revolutionary developer tools. We have two currently. It's JRebel, which allows you to reload your code changes in Java immediately and don't waste time on restarting your JVM processes, and XRebel, which is a lightweight Java profiler, which is really cool. So before we start talking about Java bytecode, let's talk about JavaScript for a second. Just don't leave. There is this tendency currently that people really like to express all kinds of negative feelings about how terrible JavaScript is. And it might be not the most refined, the language with most refined semantics or the most clear design, but there is one thing that goes for JavaScript, and this is portability. Right? It is basically the assembly of current web applications. It's available everywhere. It's available on all the platforms. You just need to fire up the browser, and it's there. So you have whatever language you have, you compile that into JavaScript, and you're good to go. On some platforms it might be slower, and some platforms might be faster, but this is the portable language that is available everywhere. So I like that about JavaScript a lot. And with that said, let's forget about that and go into proper environments. So this session is about Java bytecode, and we'll start with trying to figure out why it's so useful and how different people or technologies take advantage of that. We'll go through the necessary parts to understand the structure of that, what operations are available, how can you create a mind map of operations, how can you read the bytecode or understand what's happening there. And then we'll go into practical examples and we'll compile different pieces of code and see what they look like in bytecode and try to decipher and pick up some common idioms about what is what. So when next time you see a piece of bytecode, you'll be like, yeah, I saw that. This is just a new object creation. That's easy. So you'll get a little bit more accustomed to this assembly of Java. And then I'll show you a couple of tools. Well, I'll describe a couple of tools which are really useful and have to work with bytecode. And we'll proceed into how you can modify bytecode and what means are available for that, and just a basic introduction into how you can build another tool that works on bytecode maybe. So we'll try to fit all that into our short time here. So essentially, bytecode, or a P code for portable code, is an intermediate, usually, language for virtual machines or for machines to execute. So it consists of certain instructions that a machine can interpret one by one, and just basically they define the operational semantics of what a certain virtual machine should do. So there are many languages that use that. Java it wasn't the first language that employed the intermediate bytecode, but it probably was one of the most successful from the earliest. So, yeah, I think it kind of covers the most immediate understanding. So one of the benefits of the bytecode is that first you can interpret that, but then you can, since you have the whole program structure defined instruction by instruction, operation by operation, and you know what you have to do, you can compile that further into more optimized code as long as you have more and more refined information about what is actually happening in the code. So you start slow, and then you get intermediately faster and faster and faster. So let's not talk about just Java. There is a number of tools that are available on the JVM, a number of languages that make use of the bytecode. So all languages like Scala, Groovy, Clojure. The elephant is a Ceylon, kind of cool language. JRuby. They all have their syntax defined. They all have their instructions, and they compile it further into the bytecode. So they use their own compilers, not JavaC. They define their own semantics, but they make use of this basic, I don't want to say primitive, but very straightforward and easy to understand operational semantics of how JVM operates. So bytecode is the language of the JVM. It's more tightly related to the JVM than to Java, the language. And that's why it's actually described in the Java virtual machine specification, not the Java language specification. So Java virtual machine specification, it's a book. Who have heard of that? Who have read it? Who knows what color is the cover of the book? This is a hard one. Yeah, so it's available in the PDF. You should definitely go check it out. There are some chapters that are more interesting and maybe more relevant to just general understanding of how things work. Like, for example, bytecode or Java memory model. But bytecode is really interesting because it defines an entry point into JVM. And it defines how you can create tools that make use of low-level semantics and enhance the behavior of any application. Right? So the general process goes like that. You have your source program, you go by the blue line, blue arrow, and you compile that into the Java bytecode, and then you load that into the JVM, use the class loading scheme, and JVM starts interpreting. It links everything together dynamically and starts interpreting things. So this allows you to specify a unique entry point that sits between the JVM and your application source. So you can abstract away whatever the program is doing, and you can have your own additional functionality attached. So if you want to define some kind of aspects that will work for all the classes or for certain classes on the JVM, the bytecode gives you this functionality because we have like every code loaded into the JVM. Everything that JVM executes goes through a single channel. Right? So we cannot load functionality into JVM without working around the bytecode. So this is a great feature, and this will make you understand better how different tools from the tooling world work, all the profilers, all the APMs, basically all the frameworks utilize bytecode modifications in some sense. So Hibernate creates your proxy objects dynamically from your model and over your tables. Spring creates everything dynamically. It all works on the bytecode level. So this is the general introduction. The Cafe Babe is the magic number that sits in the beginning of every class. So if you ever need to find a class in a stream of hex characters, just look for that, and it will be a good indicator that the class starts here. So now let's go into details. JVM is a stack-based virtual machine. What that means is that there is essentially when the bytecode is interpreted. So the functionality that we want a JVM to execute are passed into the in some form of like sequence of instructions. And what they do, the JVM creates a stack which is initially empty, and then it starts loading and unloading values on and off the stack. So everything is everything that happens within and with the stack is defined by instructions. So if you have here a simple example of an empty stack, and if we execute something called push one, on the top of the stack we'll get 1. So there is no bytecode instruction called push. But we'll see this example is really useful because it illustrates that Java virtual machine is tightly related to the reverse Polish notation. So reverse Polish notation is when you first specify the arguments of a function and then you specify the function itself. So if a normal infix operation would be 1 plus 2, and that would be 3. So in the reverse Polish notation, that would be 1, 2 plus. Right? So in the same way JVM operates, first you load your arguments on the stack in any way. So you use stack modification instructions to load the values there, and then you execute some either mathematical operation or any other operation, and that modifies the values on the stack. Obviously, a Java virtual machine is a little bit more complex than just a single stack running up and down unboundedly. So essentially, you have methods. So the functionality in Java code resides inside of the methods, even if that's initializer or static initializer. It's really on the bytecode level, you will get either init method or class level init method called cleanit. And in the thread, there will be dedicated a new stack frame, inside of which you will have the following things. You will have the operand stack, which is where you will load and unload values and on which you will execute the instructions. You will have a table for local variables, which makes sense because you can have a magnitude of local variables and you can store some information there. And retrieve. And obviously you will have some kind of constant pool where all the predefined, constants will be set. So if you have a method name that you want to call, that will sit as a string in the constant pool, and just to use that, to leverage that, instead of specifying the string as an argument all the time, you will just specify an index into the constant pool. So that makes all the operations that we have in the Java bytecode much easier. So it's a bytecode, right? So every operation is represented by a single byte instruction, which means that there are how many instructions possible if they're represented as a byte? Exactly, 256. Who knows how many instructions are actually in use out of that range in the JVM? A bit less. I'm not sure about the exact number. I think it's 180 or something like that. Maybe a bit less. Some of the ranges within this single byte area are reserved for future use. So, as in, for example, in Java 7, they added an invoke dynamic bytecode instruction, which made possible and made all the integration with those dynamic JVM languages much easier. So they added that and used one of the byte values that were reserved previously. Some of them reserved for debugging, but in general, we'll have the following instructions. All of them can be divided into several groups. So first group is essential. We'll be manipulating the stack. We'll be loading values onto the stack. We'll be removing them from there, and kind of any stack control manipulations. And hand in hand with that will be local variables. So since there are just two locations where you can store data, well, actually 3, you have object fields as well. But essentially, it's either on the stack and you want to manipulate it, because if you don't need to do anything with this particular piece of data, you don't put it on the stack. Either it sits in the local variable or you put it somewhere in the field. When the method has reached its end and the execution is finishing, then the whole stack frame is collapsed, destroyed, and thrown away, which makes storing data in local variables quite not very durable. Second, the most important thing would be method invocations. Naturally, we need some way to tell JVM that, whoa, currently I want you to go and execute this print line method on the object that resides in the field called out in the class called system, and please pass this string as a parameter. So in Java, on the source code level, that is kind of like very fluent. You just specify everything left to right. In the bytecode, everything will be backward. And we need a magnitude of method invocation instructions to allow JVM exactly know how to process this method, because if you call a static method, the JVM will go and say, whoa, I know where the method is, I can link it statically, it never will change, let's do that, let's inline this invocation. If it's not a static method, for example, JVM has to jump through hoops and figure something more. We'll have, obviously, the control flow. Well, you can't build a language without the control flow instructions, but it's really not the most convenient. So those are all the jumps, all the if statements. We have the primitive arithmetic instructions, some synchronization primitives, and we have ways to handle exceptions and returns from methods. So those are the area. The most important will be the first two, and we'll focus on those right now. Yeah. So let's start with stack manipulation. We have a small number of examples here, which should be pretty clear. So they go 1 to 6. For example, if we have the instruction listing that goes from duplicate to pop to swap to duplicate x1, duplicate 2x1. Confusing, and those are actually not the operation bytecodes themselves, right? So in the JVM, they will be represented by numbers. So I think instruction to load a reference onto the stack would be, I think, 19, but I'm not sure. I hope it's 19, not to just. So yeah, those are called opcode mnemonics, and they are there to make bytecode human readable, right? JVM doesn't care about how to name that, but for humans, it's much easier to have some semantics defined. So if we have the stack with A and B, and A sitting on the top, and we call it duplicate instruction, then we just take the top value and create a new one. So our stack grows, and there is the same object, the same value on top of it. Obviously, the reverse instruction will be pop, and we can just remove this A. We can swap the top two elements, which is pretty straightforward. Then we can do this really interesting thing. We have a duplicate instruction, but we take the first one, we skip one value and duplicate the next one. This is kind of confusing point, and you will find like loads of instructions in the JVM. They don't make sense initially. So for example, the second one would be just skip one and just go, so just skip one, skip this B, and duplicate those in there. Very confusing. Why do you need that? Who knows why do we need instructions that operate on two stack cells? Because we have variables and we have types that are of different lengths. So if you have int, all the stack cells will be ints, right? They will be 4 bytes. And if you have double values, for example, they take space of 2 ints, and you cannot just fit them into a single cell in a stack. So you'll have to load them by 2 different parts, and they will reside back to back with each other. And you will know, or JVM will know, okay, this is byte, right? Those 2 values come together, but what you need to do, you need instructions to manipulate them, say, atomically. So not to actually go and figure that those two come together every time you want to do something with them. So the kind of instructions would be confusing. I think the best way, the best place where I go to look what a certain instruction mean is surprisingly Wikipedia. They have a really nice article on that. They have all the lists, they have examples, they have the documentation for the bytecode, which is quite good. I go there more often than into the official virtual machine specification. So we have basic instructions to execute the stack. Now we'll have the duality between the stack and the local variables. There are two types of instructions. So there are reads and writes. If you read will be load and write will be store. So this is the semantic of all the instructions. They will be changing based on what JVM type they operate on. So there will be the prefix. So if we say that we work on references, on object references, the prefix of the instruction will be A. So the instruction in the view that looks like A store with some parameter that takes the top of the stack. So it takes the value of the stack and stores them into a local variable by the index n. Right here, since we're talking about saving data into local variables and further, you have a put field instructions and put static instructions to save variables from the stack into the fields of certain objects. Respectively, if you have load instructions, so for example, a load, that will just go into the local variable by an index that you provide and load that, whatever the content is, and put it on the stack. And get field and get static would be the corresponding instructions for the fields. So now we kind of understand, or we should understand, how to manipulate the stack and how to put values on the stack or remove them from there. So this is what we covered yet. Let's go back to the types and to the prefixes, because this is a bit confusing. How many data types are available in the JVM? This is something that discriminating Java developer who knows a lot about bytecode should know. So there are, I think, 9. I know. Yeah, we won't cover void. So void is not a data type. So there are 9 and void. So there are 8 primitives: boolean, byte, short, float, int, long, double, and we have a reference. So in the JVM, there are actually less types. So all the small types, all the short types, like boolean or short, will be represented as ints. So every instruction that operates on them will have the prefix I. So for example, if the instruction that we want to execute adds to integers, and that is with a mnemonic of add, to add to integers we'll have I add, or to add to floats we'll have f add. So we have longs, floats, doubles, and for reference we have A. When you look at the descriptor and signatures and everything, those would be, all types will be represented by certain letters. The mapping is not exactly one-to-one, so you can see, for example, long is J, and well, chars and shorts are represented on the JVM as ints, but we have them in the descriptor because descriptors deal with meta signatures that are specified in Java language. So those will be more broad than the JVM type. And on the right, you can see how many spaces on the stack that given value takes. So there are 2 that are longer than others. Those are, well, long, naturally, no pun intended, and double, surprisingly. And for those, we'll have to use a different set of instructions to manipulate the stack values. To illustrate the point of those prefixes, here is a simple table of mathematical operations and the instructions that you have available in the bytecode to operate things. So all of them take 2 arguments. So you load the first argument on the stack, then you load the second argument on the stack, and then you execute the bytecode instruction. So quite simple. I think this is very straightforward. You have a prefix that specifies what types we're dealing with, and we have the instruction type. So the_add, for example, will consume four 2x2 bytes on the stack, add them together, and load the new value on the stack. So you will have the result there, and then we can load that into a local variable, for example. That would be a common occurrence in the examples that we see later. So at the same time, we have the conversion table, and we can convert values into different types, just so JVM knows what we're dealing with, and it can optimize our execution further. So if we always convert something to double, say, then the JVM knows that there will be double, and they just roll with it. So up to this point, we know how to manipulate stack. We at least understand that there are some instructions, and there are loads and stores. This is one thing that if you take one thing out of this, before this point, there is load for loading instructions onto the stack and stores to storing them back into local variables. So we get into the methods and method invocations. And those are the most interesting. And they have a bunch of different invoke instructions. So the invoke static instruction will, so all of them work in the same fashion. You load the arguments of this invoke, what method you want to invoke on the stack. So for example, you load the method by loading the reference in the constant pool to the name of the method onto the stack, and then you call, oh, please invoke. Invoke instruction is received by the JVM. JVM goes into the stack, looks what values are there, figures out what method to call, and calls it. Why do we need many of them? Because JVM calls different methods differently. So static methods can be specified, they cannot be overridden or overloaded. So invoke static instruction is reserved for calling static methods. So JVM exactly knows where this method resides in memory and just goes straight there. Instance methods and normal methods with dynamic dispatch that can go into different subclasses called through the invoke virtual. That is the most normal method invocation of a non-interface class method. So if we have a concrete class specification and class hierarchy, and we say, please, on this variable, which is class, say, array list of something, call method remove, the JVM goes and knows and locates the most specified remove method in the class hierarchy of those array lists and calls it. So there is a different invoke interface instruction, which is a little bit different. It is used when we call method not through the variable of the exact type with a strict class hierarchy, but if we call it on the interface. So we can define certain values in the language, in Java language, as being an interface type, say list, and we can use them and just say, please, my variable of type list, remove this element from yourself. Why JVM has two different instructions? Because it has to execute things differently. If you have a strict class hierarchy that you know where will be, the methods are at a certain offsets, right? So the new class the subclass can only add methods to the list of methods from the superclass, right? So you can always say, okay, I need the remove method. It is at a certain offset, and I know at which offset it is because it comes from the superclass. So let me just call that location. So this is pretty straightforward and efficient. With the interface, you can go different routes. You can have two classes extend a single interface, and then we'll add different methods so the offset wouldn't match or might not match. And for that, invoke interface instruction will have to do a little bit more work to figure out the exact location of the method to call. Now we have the invoke special, which is reserved for a very small amount of methods. So that would be methods of the superclass, which starts super dot something. Those are constructors, and those are the default methods in the interfaces, if I'm correct. I think that should be correct. So since there are very limited number of methods that we can call with invoke special, JVM can figure it out and call the methods very fast. And now the fifth instruction that we have is an invoke dynamic, which is it was added in JVM in the Java 7, and what it does, it dynamically figures out what is the call site and the method handle of the instruction. So not just like what method we want to call, but also from where do we call it, because of that there might be slight differences. So I don't want to get into the details of how that works, but it just determines not just arguments what to call, but the call site together. So that corresponds to our necessary knowledge for the invoke instructions, and we can go into and look into the examples. So we will use Java P to decompile the.
Excuse me, about the invoke dynamic, if I may ask.
Sure.
It was, as I understand, it is used for calling lambda functions, but it was introduced in Java 7. What was it introduced for at the time?
Okay, the question was that invoke dynamic is used for and utilized in calling lambdas, and lambdas heavily rely on the bytecode level. They are represented as method handles and references, and they are invoked through the invoke dynamic instruction. But since invoke dynamic was introduced in Java 7 and lambdas in Java 8, what was the reason for that, and what did we do with invoke dynamic in Java 7? This is a good question. So first of all, the invoke dynamic instruction was introduced not just for lambdas themselves, but to utilize and better utilize the dynamic languages. So dynamic languages, when you call different methods, and the invocation of what exactly the code that you want to run is determined not just by the name, but where from you call that. Is really heavily used in dynamic languages. So JRuby, for example, they did a great job of testing the performance. And if you run JRuby with Java 6 and Java 7, you will notice a really noticeable speed up and increased performance. And on top of that, so they did that JVM languages because they really love to innovate. They ran into that, started using that. The JVM team figured out the performance issues and how to make it better. And in Java 8, they fixed some things and made it even better. So, and started using those for lambdas. So that was, a pre-release for lambdas, and that made life of dynamic languages much easier. So let's get back into Java P. So Java P is a command line tool which resides into JDK directory. So it's pre-built and pre-shipped with the JDK. What it takes a class file, and it prints out the information about this class file. So it can show you the bytecode of the methods. It can show you the internal signatures. It can show you the local variable tables, exception tables, basically all the information that you want to know, like what sits in this class. And it does that pretty easily. So we'll go through a number of examples and see how Java code compiles to the instructions and start figuring out. So we have a really simple class with a simple method called work, because I'm predictable like that. It takes an int and increments this int and returns that. Very simple. So if we run Java P, if we compile this a.java file and call Java P on the A class, we will see the following output. Hope it's visible to you. So what we see here, we have the default constructor. It is not specified in the Java code, but it is generated on the bytecode, so it's much easier for JVM, and less magic is involved on the JVM level because all the specified methods are in the class. So what it does, it loads this instance on the stack. So it calls the init method of the object, because the empty constructor can respond just to calling super of the class, and since we have no super class, that would be an object. So we call invoke special on the constant that sits in the constant pool by number 1, by the index of 1, and that is conveniently commented here that it is the init method of the object, and we return the resultant thing. So this is a pretty straightforward, and you will see, if you look at the bytecode, you will notice this pattern very, very many times. So whenever you create an object, it will go through the following stages. You need to load something on the stack, and like whenever you call any method, you need to load something on the stack, and then it is followed by an invoke instruction, and the result will be on the stack. So it's either return or you can continue with your code. So this simple example of I plus 1 will be converted into the following code. So I load 1. What it takes, it says that we deal with an integer. We deal with loading and reading information from a local variable onto the stack, right? So loads were locals into the stack, stores were stacked to the local variables. And we load the first one, and this is the int. So by the index 0 will be referenced to this, naturally. By index 1 will be the first parameter. So we load 1 on the stack. We load the constant of 1 on the stack. So since several integers, for example, are used much more often than others, so say zeros and ones are used so much more often than 137, or 17 for that matter, there are instructions just to load that in a single instruction. So usually that would be the other way to do that would be to create a constant in a constant pool which is equal to 1, then invoke iLoad or loading constants from there. So and then we add those two using iadd instruction, and then we return the int result. Very simple. Who is confused by this example? That's good. Nobody's confused. Very straightforward. Who cannot see this example? Just checking. Okay, so now a different question. Like, what would be if we just replace that and we return 17 plus 1? To do this, so we had the I, and now I want to show you how constant loading is working, right? So it should load 17, then it should load 1, and then it does iadd. So surprisingly, this is not exactly what happens. What happens is that Java-C, when you compile your Java code, it is not very sophisticated compiler. It doesn't do any optimizations. Well, it doesn't do almost any optimizations. And all the decisions about like what is fast or what is reasonable or not, all of those are deferred into the just-in-time compilation happening at the runtime. So basically, mostly it usually just translates your source code into the bytecode as it is, one by one. But with such simple instructions like here, which is you can always say that it will be 18. What it does, it just takes and loads that on the stack and returns. So the bpush instruction takes a byte as an int. It takes a byte value of 18 and pushes it on the stack as an int. Why does it push it on the stack as an int? Because bytes are represented as ints. So the instruction will be bpush. It also instructions like cpush for char to int and so forth. So you can see the constructor code is the same. So, and it will be the same for all the classes that have the default constructor. So now ALOAD 0 invoke special 1 and return, or invoke special a different index and return would be a common idiom that you would recognize in the code, and it will be like, oh, this is my default constructor. Cool. So next time you try to debug some issue and you have to go deeper into the bytecode level, you just go that. Now let's call a method. So this example will call a method called systemout println and print this I variable. And on the bytecode level, it looks a little bit more complicated. So what we do, we start, this is a perfect example of operating on the fields of the objects. So what we do, we take the value of the static field with the instruction of get static, and we give it a reference to constant pool. And this is the field system.out of the type Java IO print stream. So conveniently, Java P annotates everything, so you don't even have to figure out what the constant pool is yourself. So we get that static field of contents, we put the first parameter of this code, so we put this I on the stack. We invoke virtual method print line. Right? This is a different common idiom that you would notice all of the time. So you load something from the field somewhere, and you call a method on that. So there is an object, and there is parameters, and there is the invoke instruction. Then we do load the constant 0 on the stack and just return that, all as ints. Pretty straightforward. So this illustrates how get static works, or put static for that matter will be the same, or get field or put field, which will just take additional argument of having the object instance on which to call. So if you really want to see the contents of those constant pools, what you do, you execute Java P with dash verbose. So a verbose output would be much larger. This is just a piece of that, just the part that illustrates the constant pool. You can see that in every class file, the constant pool is quite extensive. So first you have all the relevant object notations, you have the strings, you have the method references, field references. We have a bunch of strings in the UTF-8, which illustrate different things. And we have those Java lang system, print stream method, and every string and every class and naming type that we use in this class available in the constant pool. So whenever operation we need to do from the bytecode of this class, we can just reference those. Obviously, we don't do that by hand, but that's how Java C generates that. Well, and additionally, if we use verbose invocation of Java P, we'll get some additional information about the method. So we have the stack length, as this maximum stack size, the number of local variables that are in use. So all that helps the compiler and the bytecode verifier in the JVM to, well, verify that the class file is relevant and not corrupt, and that JVM wouldn't blow up with that. So if you need more information, Java P verbose. And now we get into the more complex method example. So what we have here, we have a synchronized block that locks on this instance. We have a field. We do some operations on this field, and we return it. So the only thing that this is missing from being the regular Java code is some method invocations, but it would be just redundant in the bytecode will be too long to just kind of put on a slide. So this part here is a constructor of A. We still have the default constructor, right? Because we don't specify anything in particular, but the bytecode is longer. And why is it longer? Because we have a field now in the class, and we initialize that during the, well, in the initial instance initializer that is inlined into the field definition. So when it happens to be in the constructor. So first we have the same idiom that loads this and invokes the object in it. After that we load that again, and we load the constant 1 and put the constant of the value 1 into the field by the index 2. Very simple. So the constructor starts as usual with a call to the object in it, and then we initialize the field. Pretty straightforward. Is anyone confused by this?
Because I thought that the initializers are called before the constructors.
No, well, static initializer will be called when the class is loading. The instance initializers will be, all the instance initializer will be combined into a single initializer block, and that will be called in the constructor. Well, it will be called after the super constructor has invoked. So we will go into object and we'll create the object first. So sorry for that. The question was that if the initializer block is called before and after constructor, or is it inline? So the initializer block will be called after the superclass constructor has run, but before any code in the constructors that you specify in this file has run yet. So if I would do a constructor, I would be able to use this field value 1 in my code. So that has to be initialized before my code runs, but it can be safely run after the superclass and the hierarchy is created. So, and after that, there is just a bunch of instructions that you have to not remember, but you want to try going with them back and forth to see how it is working. So this is now not a huge bytecode listing, but this is bytecode that corresponds to the method work, which is just a couple of lines long. So you can see, obviously, most definitely, the just-in-time compiler will optimize that and will just generate the proper efficient code anyway. But on a pure bytecode level, adding something as simple as a synchronized block just generates tons of instructions. So it wouldn't affect the performance in the long run, but the size of the code is affected. So if you, for example, know that your just-in-time compiler inlines methods that are, say, 255 byte instructions, fewer than 255 byte instructions, and you just go beyond that scope, beyond that size, then your method might not be inlined efficiently, and that would be a performance issue. So you want to check that if you're really, really deeply into performance problems. There are many ways of increasing the performance before that, but well, a curious software engineer can go and look into that. So what we have here, we have a bunch of instructions that operate on the fields and everything. What I want to outline here is monitor exit instructions with a corresponding monitor enter. So the synchronized block generates a lock on this instance, and the thread that will be executing that obtains that lock on the bytecode level that is corresponded by monitor enter and exit instructions. And you can see that there is some go-tos in the bytecode listing. So when we reach this go-to, we just jump to instruction 26 and so forth. Unfortunately, I'm a little of time. I really want to show a couple of tools for you. So we'll go further. Well, this is as straightforward as previous, just longer. So if you want to obtain bytecode of the classes that are loaded into a JVM, well, naturally, you can just go and grab a jar file that specifies those classes. But this is not exactly the same because, well, on the JVM level, you can have like frameworks that manipulate the bytecode of the classes. They can generate proxies and everything. So if you really want to see what bytecode has been loaded into the JVM, what I would recommend is to go to your JDK home directory and execute the command. So in the sa_jdi jar, there is a class called hotspot debugger. It's a really awesome tool. Like I just recently became aware of its existence. And it's really cool. So it can do different things for you. But one of the menus under that will be a class browser. And you can just like click a button, and that will generate the bytecode of all the classes as they are loaded into the JVM as there are right now. So you will see the Hibernate proxies. You will see the bytecode of what the different tools generate for you, and you can just look at that at your leisure later using your IDEs or just pure well, Java P to see that. So this is really useful tool and really cool. Another really nice thing and tool I want to tell you about is a Git watch. So it doesn't operate exactly on the bytecode or just the bytecode, but it integrates, it's a log analyzer for hotspot Java just-in-time compiler. It consumes the log files that your Git generates. You have to do a bunch of hand waving to make those logs available. But what it does for you, it analyzes, it can map, if you do everything correctly, it can map your source file, your Java code, into the corresponding bytecode, into the corresponding machine code that was generated by just-in-time compiler. So not only you will have the mapping to the left, mapping to the left to the source code, but you will see the exact instructions and you will see what the machine code is. I'm not sure how useful that in regular life, but it's a really interesting piece of trivia. And if you have some doubts about like, oh, is my code compiled into machine code correctly, or is it compiled at all, you just go and look into that. So Chris Newland created this and then donated into the Adopt OpenJDK project initiative, and it's freely available on the GitHub. You just clone that and run that. It's really cool to see what happens in the JVM. So, and we go really quickly into the bytecode manipulation techniques and tools. So obviously, bytecode is represented as, well, a binary file. What you can do, you can load your favorite hex editor and just hack away those instructions. There won't be any opcode mnemonics or anything, but you can, well, with decent skill, you can maybe just figure out what corresponds to what and just go and hack away with it. I wouldn't recommend doing that. There are plenty of tools that are created for the exact matter of manipulating the bytecode. There are different libraries for that, for generating bytekit, for simplifying the bytecode generation. Like say, there is JavaScript, which allows you to specify your Java code as a string, and it will compile it into the bytecode on the fly, which is really cool because you don't have to actually use the bytecode instructions. There is a ByteBuddy, which we'll look in a minute. There is ASM, the most probably low-level tree visitor pattern-based bytecode manipulation framework, and others. So, in a nutshell, whatever you will, like all of them, most of them, will look something like that. All the frameworks, and this is an example of using ByteBuddy to generate a dynamic class, and to obviously, since this is a dynamic class, the only representation that it has is the bytecode, right? There is no source code because on the JVM level we can as easily generate the bytecode directly. So what we have here, we just say we want a new dynamic type, so let it extend from the object, and let's intercept the method to string and return hello world from the value hello world whenever we need that. So, and then you just have a bunch of default instructions to convert this ByteBuddy class interpretation into the actual bytecode that will be loaded. So you'll have some kind of like class loader, and you just need to load that, and after that you can just have this dynamic type class instance, and you initiate the new object, and you can call to string, and indeed it will be hello world. So this is actually how more or less the bytecode manipulation works. So people don't use hex editors. They don't actually remember all the opcodes. Some people do. They are really smart and have great respect for them. But my head is too small. I barely can figure out like what I have to do functionally without translating back and forth. So people create those tools to have a higher level abstractions into the class interpretation and the bytecode. So yeah, you have those high level abstractions. while this is really cool and useful in the industry, since we are here on the bytecode related session, I will show you another tool, which is less useful. Well, it's really interesting, less user-friendly, but more easier mapped into the bytecode instructions. So it's called JavaScript. It's freely available on GitHub. It's a library, so you can just like load that from your favorite, I don't know, bin tray repository or Maven Central, or whenever you take your libraries from. What it looks like on a class level, it has this DSL that maps the bytecode instructions into the Java code. So you have a Java code that is mapped to bytecode, like basically one-to-one. So what you say, I want to define a new class, and I want that class to have a method main, which will be both public and static, with signature like that, which will return void and take the array of strings as an parameter. And the code block that will describe the body of this method is, please load constant hello world. Then get static field, get static is a bytecode instruction for getting fields, right? Get static called out on the system class, and we expect that to be a print stream. Then you do a swap. I'm not sure why exactly that swap there is, but well, you can do a swap. There is a swap bytecode instruction, and you can just call that. And then you invoke virtual, and you pass all the parameters, and you return. So this is really great example of how to maybe get into this bytecode or understand bytecode easier. First, you can read that, but reading doesn't give you that much. What you want to do, you want to experiment and like just maybe see what happens if you swap different instructions in place. Maybe you get a different program that is functionally incorrect, but still produce some result. Would be really cool. And on the Java level, that is much easier to do. You have the IDE autocomplete. You have all the tools to go there, and you just roll with it. So I encourage you to take a look at JavaScript if you are interested, and just go with it. Obviously, if you want to do actual manipulation, go with libraries if you need something industrial. So now we have 3 minutes to really quickly go into Java agents, because reading and manipulating bytecode statically at your leisure when you have no program running is really cool, but not very interesting. What you actually want to do, you want to intercept the class loading scheme and modify and manage the bytecode and just rewrite that on the fly while the classes of the application are loading. So you load the class from the bundle package and you create this Hibernate proxy, like a boss. So for that you would need a Java agent, most definitely. So it creates, it consists of a couple things that you need to learn, but basically it's a jar file where a certain class with a certain name pattern called pre-main is specified. There should be a manifest file, and you will need a Java agent parameter to run that. You will get access to the instrumentation API, which specifies class file transformers, which you can register. And those are really cool beasts. They can intercept the class loading scheme, and they will get the access to the byte array of the class, and they have to return the byte array of the class definition, right? So they have the class, they can just pass it through and just define the same class, or they can just do something on the fly. So, and an instance of this transformer would be, well, it would look something like that. You just define this single method. Using the instrumentation API, you will register this myTransformer instance to intercept the class loading, and you can do whatever you want with that bytecode. You can use JavaScript, you can use ByteBuddy, ASM, JavaAssist, whatever framework you fancy. You can just change bytes on the fly, like in hex, like a savage, basically. And they will return that. So, and you can do everything. You can add your own functionality to JVM very easily. So for the further information, we have a couple of really interesting pieces of content on RebelLabs blog. So we have the report covering basically the same story, and, but a bit deeper and in more detail, probably less, more coherent, say, mastering Java bytecode at the core of JVM. It was written by Anton Arhipov, who is a Java champion, who is currently the product lead for XRebel, at that time for JRebel, so he really knows his things about Java, about bytecode. You can see it by the link. You'll have to fill the form, but that's painless. I'll upload the slides, so I'll have to show another resource in 40 seconds. So we also, at ZeroTurnaround, Simon Maple and I usually host those virtual JAG online Java user group sessions where top world-class speakers come and present sessions. And recently, Raphael came and delivered the Java bytecode and practice session, and I used a couple of his slides in this session, in this presentation as well. So on the VJAG, and you can just Google virtual JAG and find him at this session. It was really interesting. You get more insight into how to use ByteBuddy. You will get maybe a different, more coherent story about the bytecode as well, and just go check it out. So you can also check out our tools that ZeroTurnaround provides. The slides will be available in, say, maybe a couple of hours because I have to fly. But as soon as I'm online, I'll upload the slides, and they will be published on Devox Poland website as well at some point of time. You can just register for the eval and try JRebel. We'll be happy if you do that. You'll receive a t-shirt if you do that successfully. And well, all in all, thank you. I'm really happy to be here. Have a great third day of the Devox. Thanks a lot for coming.